Thanks. So let me continue after this cohomological introduction from yesterday with actually the results on the Drinfeld tower. So my talk is going to have three parts today. So first part is a multiplicity results. Which we like to call pointwise results. And second, factorization. But finite level. So we are on finite level of the Drinfeld tower, and we factorize certain version of completed cohomology, but we completed cohomology in the C direction. So this is all finite level. And these two results are written down, and they are on archives. The third one is in progress, and this is completed cohomology ad infinity. So also factorization. And here I just mentioned some pointwise result today. So in progress. In progress, and this is at infinity, on the infinite level. So let me start with the, so the way the logic goes here actually, so these pointwise results are key ingredient here, but also because we understood much better what we were doing when we were writing this paper. Then there are some arguments here which actually simplify this first paper a lot. So I will present the simplifications. Let me start with multiplicities. Okay, so we specialize the setup here. So we have K over QP is now finite. And G is going to be GL2 QP. And that's maybe all I need for the moment. And let's look at an example then. So the bottom layer of the Drinfeld tower, which is just the Drinfeld plane. So we denote it this way. We take pi1 and we are going to look at the geometric cohomology, so the geometric plane. Maybe I have the usual notation here, so GK is going to be the Galois group. I'll say GK. Oh, that's you. You are right. It's K. Thanks. So some of the results, many of the results we have holds for this in, but we will specialize to QP for the full results. But for the base case, it doesn't matter. I can just do that. So the base case, we have the following computations. So we are interested in computing. We are interested here in finding realizations of p-adic local Langlands for GL2 QP in the etale cohomology of this tower. So if you look at the etale cohomology, so that was the first computations we did. This is continuous Steinberg QP dual, and here the continuous Steinberg are continuous functions from the boundary mod the constants. So we have this computation in the paper. So let me mention why. It's a very elementary computation. So you use Kummer theory plus vanishing of Picards of these basic affinoids, let's call them that way, basic affinoids, which cover the Drinfeld, standard affinoids which cover the Drinfeld space. So this result was this similar kind of computation. I mean, the result was known for L different than P. It was a computation of Drinfeld, and he also announced it for P. It's kind of funny because we believed what he said, even though his proof was not correct. So, but if you look through our papers on not this one, but some other papers on the subject, very many computations we use are actually going back to the work of Grosser-Kroner, who was very influential in computing cohomologies of various spaces of related to representation theory, and he basically had all the tools to, for example, compute cohomology of the Drinfeld, p-adic cohomologies of the Drinfeld space, but he didn't, and he didn't because he didn't believe. He knew there was a mistake in Drinfeld's argument because Berkovich told him, and then he decided the result is wrong. So he didn't follow. But the result is actually correct. And once you believe it, you can prove it. And I'm sure he could have done that easily. Okay, so a couple of remarks here. So in some sense, of course, the example. So this is an example of a p-adic period domain. And the p-adic period domains, like all the period domains, are extremely simple. So they're very misleading. In fact, what happens in relation to what happens to the with the coverings. But here you can also see that, of course. So first of all, this etale cohomology, let me make this remark. Well, first remark is that it's reasonable. So that was a good sign, but again, maybe misleading. And now as a G representation, or as a, yeah.
No.
Let me do this.
In this to your point, I mean, it's just you have the GL this way. Not the bad basically.
It's C.
You were Mondo.
Oh, no. Now it's C. Let's see. Yes. So as a G representation, it is co-admissible, which in the language of Schneider-Tentelbaum means that admissible means that there is some finiteness condition with respect to the Wiesława algebra. So we have it on this level, as you can see, but we are not going to have it in the towers. So. And if you are interested in the Banach-Colmez type of phenomena here, then you see that all you are getting here are QP vector spaces in this cohomologies. Well, it's a toy example, but for us it was important. Okay, so that was the base. Now we pass to the towers. I need more notation, maybe. Notation. So G check is going to be units in quaternions. OD maximal order and omega D uniformizer. Okay, and now I'm going to draw, maybe I draw the Drinfeld tower here, but I'm going to simplify the picture. So this is approximate pictures. I'm going to ignore the fields of definition, the veil descent, and just write it the way it should work, but it doesn't quite. So M infinity is just my notation for the tower. It doesn't mean anything. Mn is the finite level, and M0 is going to be the Drinfeld space itself. And we are going to be interested in this level at the moment. When when we are interested later on in the perfectoid version, I will put hat here. So since I modified this well enough so that I actually have a Galois action, so I have a Galois action here. I have action of G and G check, and the Galois group here is D star mod 1 plus T. So that's going to be my picture. And again, all the cohomologies now for these two first parts are going to be taken in the naive sense. So we are going to take the cohomology of M infinity C. If it appears, it's just going to be limit of these cohomologies, colimit of finite levels. And everything is going to be geometric. So sorry if I skip C, there, still there. So if you are careful, I mean, if you are interested in how this thing is done carefully, then you can see in our paper we have to mod out by some subgroup to get all these structures in the right way. Okay, yeah, so that's the picture, and let me state the two multiplicity, the pointwise multiplicity theorems. So the first one is in the first paper. So it's V multiplicity. V refers to Galois representation. So L, we need to work with coefficients because of the coefficient field of the Jacques-Langlands functor. So we have to extend the coefficients. V is representation of the Galois group of QP, absolutely irreducible, and dimension at least 2. So let me state this in this way. If V is, and I will explain what these things mean, supercuspidal, dimension 2, hot state weights 0, 1, then you have the multiplicity you would expect. So if you look at GK equivariant maps into H1 etale at infinity. But you remember this infinity is, there is some Tate twist, the coefficients have to be enlarged, the infinity is kind of fake, right? The infinity is just an inductive limit. Then you are getting Jacques-Langlands tensor, and this capital pi V is always going to refer to p-adic local Langlands. Yeah. Everything is QP now. I already changed over.
Did?
Ah, yeah, thanks. QP. Oh, right. Okay, and second, otherwise, this is 0. Okay, so one multiplicity, and maybe I have to explain, should explain here what are these things. So let's start with local Langlands. Well, it doesn't appear there, but it is there in some way. It's an infinite dimensional representation associated by local Langlands functor to the Veil-Deliny representation corresponding to V, and then Jacques-Langlands of V is just the Jacques-Langlands of this. So infinite dimensional, finite dimensional, and then V supercuspidal just means potentially crystalline here. So n is 0 on dPST of V, and what else? LL of V is supercuspidal in the in the usual sense. I think that's all I need here. And now capital pi of V is going to be the p-adic local Langlands of V for G. So representation of G. Okay, so it looks exactly like you might guess. If you are very optimistic, it should look like. Okay, so maybe I add a couple more remarks here. So we have this DPST guy here. So from p-adic theory point of view, we have DPST and we have filtration. Some things here depend only on DPST, and some really need the filtration. So they deline local Langlands depend only on DPST. And of course, the whole thing doesn't. So pi v depends on the whole of v, which means by p-adic theory, it's DPST plus fil1 of d de Rham of v. So from the point of view of the cohomology theories we are using here, the DPST is going to be recovered by Hyodo-Kato. The filtration will, of course, come from the de Rham cohomology, and we have to interplay these two to compute this thing. And one more thing, that local Langlands of V is the p-adic one mutex smooth vectors. Okay, so that's the picture here.
So according to your technique of hospital, like you have to sum up the factors, video and the height that don't sorry, stuff that you don't have.
Sorry?
But that's my level.
Yeah. No, but
And I was to yeah. I think you should take the other music the best was that yeah, it's really but I didn't that forget. Okay. It's okay, I can.
So you mean the implication is just one way, it's not an equivalence here?
Right. Way that.
Not.
Yeah, this.
Okay. Sorry, let's put this. So now I would like to state the second multiplicity result, and this one was is important for the factorization, total factorization. So okay, let me state the second one. So now M is going to be my notation. So we are going to work with phi n GK modules, but we are going to extend the coefficients to this L. We have to do it everywhere. And rank 2 over now these are going. So remember, this guy here is always over QP NR. So we have here over QP NR L, if I'm not mistaken. Okay, and theorem. So we tend to fix this M's, and now this is, so let's call it 2 maybe, pi multiplicity so V is now representation of, so V would be a representation for the Galois representation. Galois representation, and absolutely irreducible, dimension 2, and then we have home. The group is G, p-adic Langlands, dual, and then again H1, and again on finite level. Okay, and now this has So two cases. So we have V tensor Jacques Langlands of M, and I shouldn't have drawn this. So let me put in which condition if V is VML. I will write the definition here, but this is the Fontaine functor, and M itself is of level n, and I will explain in a moment. Okay, and 0 otherwise. So again, you see what you think you should see, but maybe I need to explain here again. So I need to explain this Fontaine functor here. So MDR is going to be the RAM version. So of M. So we tensor all the way up to Q and then descend. And L is a line in MDR line over L. So L line, and now Fontaine as a functor which takes this data and gives us Galois representation. So we get, I will write it this way: M tensor over QPNR B crisp plus phi equal P, because there is some twist somewhere, and we take the filtration one part, which I just write as intersecting with L, and M of level n. It just means that M is kind of visible on this level n.
Is it?
Huh?
Here it is.
Is M irreducible?
One thing is what it will do. Yeah.
Where does it appear in the definition? Here in the statement. I need to assume here to be irreducible. Thanks. Maybe it's in the definition of level n, actually, in this statement. Thanks. Okay, so these are maybe this was all I wanted to state. Maybe I just mentioned a remark here. So this theorem 2 is so I'm going to focus on sketching the arguments for theorem 1. But for the theorem 2 is proved by the same techniques as theorem 1, actually claim 1 of that theorem, claim 1. So the first claim of the theorem, not the second. And let's now start with the proof of this theorem 1, claim 1. Okay, so let me sketch the plan of the proof. So plan, the way we see, so I don't remember when the first paper appeared, but the way we see the proof now is quite different from the way it's written, actually. So let me just sketch how we see it now. So step 1 is the same. So we are interested in etale cohomology, but we are going to actually mostly compute with pro-etale, so we can pass to pro-etale cohomology. Step 2. So remember last time, we are talking about coverings of Drinfeld space in dimension 1, we know, in fact, in any dimension, we know that they are Stein. So we are in Stein case of p-adic theory. So can so we are going to use the fundamental diagram I sketched last time, and we are going to identify. So we have to identify the terms in the fundamental diagram. And when I'm saying that we understand things better now, is this step that we understand better because we understand cohomological theories better, p-adic cohomology better, so we can simplify that part. And then in the third step, identify the Breuil-Strauss diagram. So I will explain what I mean here. And in step 4, you just compare the two. And you see that they are the same, modulo that there is, yeah, well, you will see that they match perfectly. Okay, so that's the plan. So let me write here what we want to prove. So I start with step 1, maybe. Step 1. So we are just working with H1. So what we want is to compute home. So let me write this way, this multiplicities. Let's say I take G-check and Galois, and then I take Langlands and VML, and then H1. I want to write it because I'm going to manipulate on this, so L1. And we want this, so if I got all the parentheses right, this to be computed by pi of this object dual. Okay. So in step 1, we claim that it's enough in this picture, in this formula, to replace H1 et al. Via H1 pro et al., which you remember is easier to compute, and to replace pi of VML with pi VML locally analytic vectors. Locally analytic vectors in this. And why? So we use two things here, that H1 et al. So this is the thing I mentioned yesterday, that in some cases you can access H1 et al. By looking at H1 pro et al. And taking G-bounded vectors. So you are applying now G-bounded to this whole thing, and now you're looking at G-bounded vectors here, and now Colmez-Dospinescu tell you what they are. So Colmez-Dospinescu. No, I said it in a wrong way, sorry. I will repeat, erase that last sentence, was inversed. Colmez-Dospinescu tell you that, that if you look at pi VML dual, then it is pi VML locally analytic first, then dual, and then we take G-bounded vectors of that. Okay, so so these two results combined allow us to put pro et al. Here, and I can put locally analytic here. And now I can use the sentence I just said, because Why I can do that is because when I apply Ig bounded vectors to both sides, these two results recover the etale version of this thing. So I can replace pro-etale here, but of course pro-etale is kind of locally analytic phenomena, right? So you're ending up with locally analytic vectors here. And this is what we want to prove.
En als ik dat het pro-etale en de water to values by vectors, so that this will also work for it of PD?
Yeah, I think that one is. Yeah. Actually, many of the things we do work for extensions, but that one in particular is. Okay, now let's pass to the next step. Okay. So in the next step, we will try to take this fundamental diagram I drew last time and try to identify it. But we don't have to identify, I mean, we will try to identify it point-wise, so to speak. So we'll try to identify just these multiplicities, which you see over there. That's what we want to do. So maybe I write this diagram here, and then I will manipulate on it. So let's write this diagram. So fundamental. So we are Stein, we have this diagram now.
Yeah.
Okay, so we have H1 pro-etale in the middle, that's what we wanted. And at infinity, and twist it by 1. And then we have this, which I will write in this way because I am running out of space. And infinity, so this is the Hyodo-Kato part, if you remember, 0. And here we will have, we are in dimension 1, so we just have all the regular functions. There is, let me ignore the constants. There should be some modding out by, okay, let me write this way. Let me put it, okay. And then I have the same object here. Okay, let me write this. Okay, now these maps can be identified explicitly in dimension 1. They're very simple. So we have exponential Rayleigh and D-log. So it's just Kummer-Dieri here. And omega 1 now, and infinity is C. And then here I have H1 Deron and infinities. Okay. So these are exact, and we have maps of 2 exact sequences. Now I have to explain more perhaps about this, so some notation here. Let's see. Right, so some notation. I will want to take some eigenspaces of these things. So if T is a QP G-check module, we are going to set Tn to be the n part. So it's hom LG check Jacques-Langlands. So by m part, we mean the Jacques-Langlands part, really. T extended to L. The T was over QP, remember? And now this Hyodo-Kato fellow, which appears on the right, let me write this here. This is the guy which we had yesterday. So it's Hyodo-Kato, M infinity, C, BST, BST plus, over QP and R. And then you have eigenspaces for Frobenius and N. And maybe let me just, so I have this notation, but let me also denote it in this way for future reference, that this is X plus ST applied to H1 Hyodo-Kato. We will apply it to other things, these scalators. Let me just put it here. Yeah.
At the beginning, you said the static activity were just Wiesława and the things, the balancing that we let to culture.
No, it's not geometric object. I just cheat all over. I mean, everything can be done on finite levels. Yeah. I just.
It depends.
Yeah.
Yeah.
Yeah. I mean, in a moment, it's all going to be. I mean, these guys will come from certain level, and then you drop to. So this is just figure of speech. Okay. Okay, I have one more board, great. So now I am going to decorate this diagram over there that I wrote. So, but I need some facts to do that. So let me start. So I fix my M of level n, speaking of this, and then I want to take these M parts here, M parts everywhere, and I try to understand this. And for a reason which I don't remember, but maybe Gabriel does, I get this disappears. Don't remember. But somehow the constant disappear. And now we want to identify these guys. So let's start with the first fact. This is it comes from the slogan I mentioned yesterday. First fact. P, thanks, P. There is one twist, very good. Thanks, P. So the first fact we identify Hyodo-Kato. Hyodo-Kato, M is M tensor with local Langlands of M dual. So why? So remember, yesterday I listed a number of slogans, and one of them was that Hyodo-Kato cohomology now behaves like etale cohomology. Well, it should in general, but in this particular case, we can actually prove it. We are in dimension 1, so this is a Velderian representation, but also you can treat all the automorphism of your original space. So if this were etale, so then you use, of course, the Laddick situation. So in your Harris-Taylor in general, both. But in this case, I think it's already Karayol. Maybe we need Saito. Okay. You have if you compare it with etale, Laddick etale, you see that you have Jacques Langlands component here, you have the local Langlands component here, and this should this plays the role of the Galois representation. So that's that gives us the handle on the Hyodo-Kato. And now that's very good because we are trying to compute this thing here. So we are trying to identify this object. Some arrow here.
Hyodo-Kato.
So we are trying to identify this object, and this basically allows us to do that. So we have Hyodo-Kato 1, 1. Now the M part. So we have this decomposition. Now, if you look at this formula, there you have to apply some eigenspaces. So what we are going to get is this ST plus eigenspace formula, but just to M's, and the local Langlands part, of course, is completely irrelevant for that, so stays out. So
for BM, yeah.
now this remember is the Jacques Langlands eigenspace actually, GLM. It's just my notation. Sorry, I know it's confusing. No, I know it's confusing, but it's much less to write, so that's why. Yeah, it's the Jacques Langlands part. Right. So we are getting out the Fontaine factor of, well, not quite, but DPST, I guess, of M and the local Langlands outside. And for the Dram cohomology, remember that Hyodo-Kato isomorphism tells you that Hyodo-Kato tensor C is, or K in this case, is actually the RAM. So what we are getting here is M the RAM tensor. We take this formula, we get M the RAM tensor local Langlands M dual. Okay. So I could simplify these two. Let's do that. Simplify these two on the right. If I do that, then now do I want to do that? Sorry. Maybe I don't want to do that. Sorry. I have to write one more diagram. Okay. But now we want more because we want to take also we want to take the line in the RAM cohomology. So fix a line L line in M the RAM. So you've seen this kind of computations already in Banchow's talk, in fact. And then we take VML spaces, eigenspaces. So let's say it this way. So let me add this here. So we have Jacques-Langlands eigenspace and then VML. So that's Galois eigenspace. Same here. And VML. And here. And VML. And here as well. And VML. And everywhere here. Same thing. So now we want to identify these two objects on the right. And now we know how to do that. So I already have this object identified. If I specify this line, I am going to actually completely kill this object here. So I'm going to get just local Langlands here.
You know, that's something exactly what people mean. You're very in that. Or if you want now, you and the resemble you the second to then to say that the
yeah, you need, yeah, I mean, definitely need to know that it's exact. But yeah, I got this local Langlands dual, right? I think that's all I get on that side. Yes, yes. And here, let me write this, what we are getting here. Here we are just going to get M, the RAM, tensor LL, and dual, and VML maybe. Sorry, I just wanted to make sure that I simplify. So the whole work here is in identifying these Hiodo-Kato parts. And
that word.
I put M at the bottom. M the RAM, tensor LLM dual, VML. We don't have any more. Sorry. No, that's not true. Sorry.
The coordinate will be seen. And because of the swing to go and border, just one that will go down. That's it.
With MDR itself?
Yep.
Oh, sorry, that's not what I have in my computations. Well, it makes sense in the diagram, though. Okay, the diagram looks better than it did. That's true. Okay, so I just want to sum this argument up in maybe 2 sentences. So we have this fundamental diagram that's from general theory. Then we have to identify Hiodo-Kato, and for Hiodo-Kato we flip to etale and use the etale data, and there the argument is global. I mean, we don't have local proof of local Langlands. So we use global methods here. I mean, indirectly, but there is a global input here. Okay, so this is what comes up from cohomology theories, plus this local Langlands. And now I have to erase something with the middle one. Now I want to recall what we get as an input actually from the Breuil-Strauch conjecture, which was proved by Dospinescu-Niziol. Okay, so in step 3, this is the second input. We have Breuil-Strauch conjecture. Okay, so let me state it in this form, in the form that we actually did it here. So there exists a bicartesian diagram. Oh yeah, so speaking of which, I should also make sure that, so this is the diagram here we are interested. This is important for us, this diagram here. And this diagram is bicartesian, and it's bicartesian, which means that if you take this map to the sum of these two and then to this is a short exact sequence, is bicartesian because we can control these objects here. So it's bicartesian diagram of that type, and here we get another one, which at the bottom looks like the same. We have VML eigenspaces. Then we have the RAM tensor LL and dual. And then at the top here, we have the same object as over there, but Breuil-Strauch conjecture identifies you the kernel of these two maps. So it puts here pi v ML locally analytic dual. And this is bicartesian. Okay, so step 4 is now, so about the proof of that, so I mentioned that there is a hidden global input here, and the proof of that is also global. So local global compatibility type of thing. And here we have step 4. Well, now that we have this bicartesian diagram and this, then we have what we want, right? We have that H1 pro etale, the Jacques-Langlands part, the Galois part is the same as pi VML locally analytic dual part. That's what we wanted. So that's the proof of the multiplicity for V the way we see it now. Okay, so this was for the claim first, which was, I erased it, but this was the multiplicity formula. But then there was the second claim that nothing else appears, right? The claim 2 was that the representation, the Galois representation, which shouldn't appear, they don't appear. And our original proof was very difficult combinatorial argument, which we simplified in the factorization paper. So, well, I don't know about simplification, but it's more conceptual, let's say. So it uses it uses claim 1, which we just shown, and it uses this theorem 2, which is multiplicity of pi v, but theorem 2 it doesn't really use, it just uses this claim 1. But then it uses crucially what I'm going to talk about soon, which is finite length argument. So finite length results, which is takes most of the factorization paper. This finite length results mod p. Okay. There are a couple of remarks I want to make about this proof, which so I mentioned the two places where you use global arguments, but let me just mention a couple more. So one, what we got was not by Cartesian, but we got a Cartesian diagram actually. Which is like that. H1, I think, I don't know. So I don't know if this is correct. Maybe my collaborators can, because when I was preparing this, it seemed to me that what we actually prove is that we have Cartesian diagram like that, but maybe G bounded vectors here, H1, the RAM, G bounded again. And then we have here the Kato part, and again G bounded. And this should be Cartesian, so it means that I have a short exact sequence. This goes to the sum of this, and goes to that, but I don't know about surjection, although maybe it is. I think we actually prove something like that, don't we? Which is why I'm stating this is because it's one of the very few cases that we can actually prove something like have something like CST for etale cohomology. Right, so we can recover etale cohomology from these objects. And this bounded condition just means that actually you are looking at really at the model, at the formal structure here.
Right.
Right. So it seems correct, right? Yeah. Okay. Don't know why we didn't state it in the, but okay. So the question here is in which generality this kind of thing. We have this kind of etale CST, or I don't know. Okay, so this is all I think I wanted to say about multiplicities, in fact. Okay, I will pass to the factorization. So now that we have this pointwise result, the question was, can we glue them, but still on the finite level? So we are still basically working on a finite level of the tower. But here, here the question was, for factorization, the question was which cohomology really to take. That is, if we, I mean, naturally it would seem that you can just, we are just trying to look at the etale cohomology of M and C. But if you try to do that, well, we couldn't understand very well what's happening there. So instead, we took something like completed cohomology, but kind of in the C tower, so in the tower of fields between QP and C. And let me state this. Define this cohomology. So factorization, but still on finite levels. So theorem 3. So R is again large enough to include basically all the Langlands of M's that will appear. So we'll have finite number of these M's, so this is okay. This will be finite. And now let me just write the statement first. We take Mn level. Now I really stick to some fixed level. Take QP bar, and I have to define what I mean by that. And now this is on the finite level. You will just see finite number of M's. So this is just the direct sum, and here is going to be multiplicity of GL of n over L. And what is this multiplicity? Is going to be finite sum, sum, but now it's going to be completed. And let me write this expression here. And I will explain what these things are. Okay, and so this is p-adic completion, and the tensors are all here over RBM. Okay. So this is what I refer to factorization of our cohomology. Now I have to explain these things. Okay, so as I said, this is completed cohomology in kind of the coefficients direction here. So let me define. It's etale, so invert P at the end. And with OL coefficients, we define it as limit over K, and then colimit over finite extensions of QP. And then you look at H1 etale, finite level, but in K, and torsion 1. Okay. Now this is a subgroup of the geometric one. So we still use properties of this to infer some properties of this, but in general, we don't know much about this inclusion, if I understand it. Okay. Now M. So first this definition. Now what is M? So this is type of level N. N is fixed now for me. So that means that okay, what do I mean by this? So what do I mean is, so M is going to be, well, first of all, M is an L phi and G QP module. Dimension 2, such that, and now I of level n means that the Langlands representation factors through the Galois group of discovering Mn over the plane, the Drinfeld plane. Now, of course, so what is a technique of proving something like that? So this appeared already in Pashkonas's talk, and here is the same. So we have to work mod P, and then you use Gabriel's decomposition, and these B's, these blocks here appear from Gabriel's theory. To use Gabriel's theory, we actually have to work very hard to prove that we are in the setting in which it applies, and that's most of the paper. That's where the finite length arguments appear. And then one has to identify these objects. So most of what I'm going to write now, or at least the beginning, comes from Gabriel's theory. So B runs through blocks of KL residue field representations of G, semi-simple, dimension 2. And I think this was explained also in Pashkunas's talk, that this can be also classified by, do I need that? Maybe I leave it here, I don't need to do that. And next thing is, what are these rings?
Ahead.
Did you out?
This appears when I classify this as an orbit, right? Okay, sorry, that's right. So blocks semi-simple. Never mind the dimension 2, then I skip the orbit classification. So it's the same with semi-simple, right? That also refers to the Galois representation, not to the, let's skip that. And now we identify these multiplicities here. So B n. So R is going to be a deformation ring, and rho is going to be universal Galois representation corresponding to this deformation ring. So we have GL2 R Bn. So universal deformation ring. Now, what types? We have the RAM, Hochstate weights 0, 1. Now, dPST has to be equal to M. So let me just assume, so this is when M is supercuspidal. And if M is special, the ring is going to be just, I think the field L, and the representation is going to be a character. So let me just look at this. Few more remarks in a moment about this ring, because that's important. So on what?
Yeah.
It does depend on B. So the universal formation of the rho bar
Yes, corresponding to B.
But the option that happened will bias the modern so to get the ring you about the frame, but I guess they need to make the figure, so I think
Clear, you remember? You don't remember? Sorry, one right.
Because then you got
No, but you have to treat all the M's, so you have to treat all the items.
Yeah.
You want me to just assume M is supercuspidal? Yeah. But we have to, in the final thing you have to treat all the M's, but. No, that's not true, right? Yeah, it's not true there, but not literally true, yes. No, I know it's better. I did lie. No, we have to treat all the special guys as well, but.
is our son over here, and that's better.
Yeah, the sum is here.
Over there. Sorry, sum is over there, yes. Good.
Okay, so that's not everything. So in the multiplicity theorems I just stated, I also ignored all the special cases of n, but you have to treat them as well. Okay, and finally there is one more point. We have pi of rho Bn interpolates the pi rho x dual for the points in our ring. So what I mean by this, if I'm going to get, I'm going to get my pointwise p-adic local Langlands. So I just want to make one. So I wrote these things. This is very impressionistic. It doesn't treat all the cases, but there are certain points that you have to keep in mind besides the details. So the important point is that these rings are extremely simple. The thing is that in this case, with these rings are very simple. We can understand them. In fact, we have some other descriptions of them, and that's one reason why we can glue the pointwise results to these global results relatively easily. So let me just make a number of remarks of that sort.
So just a quick question. So it's finite level, right?
Yes.
That ready to go with that pilot tools at somewhere else in bio.
Sorry?
I said like to get the kids for better plus. Now we get some narrative with zero one. Just way that we got. Okay, those are the little agent I think there's no about it.
No, the level refers to the quaternions. Is that what you were asking?
There's no I was thinking. Silly. That you go on out. Feeling valid, so fine. Hold the left out of it.
Okay, so the remarks I want to make. So, of course, this decomposition is inspired by similar decompositions for other types of completed cohomology by Merton. And there are some analogies which at least to me were helpful. So inspired by Merton's results.
That's fine. Art. Again.
Oh, this is dual. This is R dual.
So, it's
R dual. So of course this is for a global situation, but anyway, this was inspirational, and the way I like to think is about this. So this object here, the formation ring. So if you look at Pashkunas's work on the subject, so Pashkunas and Pashkunas, I think Tank, they actually prove R equal T result, right? And this ring here corresponds to Hecke algebra in this philosophy, and this Hecke algebra, the way I think about this Hecke algebra is as the center, so basically as the endomorphism of the projective envelope corresponding to the block B here. the same B. So these are some kind of local R equal T results. This is, of course, just very impressionistic, but it helps to understand what's happening here. Now these rings, so these rings are basically, the deformation rings are basically constructed by Kissen. We have some other definition in this simple case. But I just want to mention how they behave. So R, in this case I just described, this is the ring of bounded analytic functions on some open subset of finite number of components. I think maybe you have to take off P1 of MDR, which is just P1. So the point is that basically you get p-adics. So this is as nice as you can imagine. So why P1 MDR? That comes from the fact that to describe representation, Galois representations, you have to work with the filtration level, so with the line, and that gives you P1 and DR. And then you have p-adics. So this is an essential input. So let me state now how the proof goes. It has 3 steps. So basically, if step 1 we already did, this is where we have this pointwise result. We get this. We use the pointwise result for phi, not for v. The second step is preparation for gluing. So step 1, pointwise. So this is already done. Step 2, preparation for gluing. And step 3 is the gluing itself. So I don't have that much time left. So let me just mention the gluing itself. So where does this formula come from? But I think what Pashkunas was talking was already quite a lot in that direction. So step 3, you need some finiteness results. And this finite left above results, and that's done in step 2, and then you can apply Gabriel's theory, and you get block decomposition of, now you have to work integrally. We look at finite level both in N and in K, and also at finite level here. But then we go to the limit over K, small k here, and we get a block decomposition of the etale cohomology M and QP bar L1. And it looks like that again. N, finite number of n's, then completed sum over the blocks, and then so outside you have a multiplicity. So this is multiplicity for Jacques Langlands. So this first part has nothing to do with Gabriel. You just have multiplicity for Jacques Langlands, and then but for the multiplicity for Jacques Langlands, we use Gabriel, and we get block decomposition completed after we passed the limit. And then we have projective envelope, and then multiplicity of projective envelope. And this is all happening over the corresponding endomorphism ring. Okay, what is that? The projective envelope, by definition, I think this is sum over elements in the representations in the block of, which is actually, I think, the dual is the projective envelope of the dual, but let me write that one. So now the question was how to identify this object, right? So let me just so by definition, the multiplicity block M is from G check, projective envelope, GLM into H1 etale, and then QP bar D1 1, okay. And the fact is now that, so in this step 2, from the step 2, we get that this object is actually a module over the formation ring of finite type. Finite type, and 2, we identify multiplicity over E of B as Galois maybe also, as home LG and this is what appears in the final formula, and the dual here. And this follows now from 1 and from this theorem 2, which was the pi pointwise. And this is the part which I mentioned that here use the shape, the properties of our ring that we have p-adics to actually put this to lift these pointwise results to the whole family. Now let me just take a couple minutes more. So let me just mention what goes into what theorems you need in part 2, which is actually most of the paper. So in step 2, so these are the finiteness theorems. So we have maybe 2 theorems. Let me state theorem which 4. So finiteness. We state that we prove that if you look at mod p cohomology, so mu p. So actually you are looking, yeah. So this is the dual of a smooth admissible representation of G of finite presentation. Okay, so you see this dual here, which means that maybe philosophically we're actually working with compactly supported, but we don't know it because we don't know any dualities like that. Smooth part is easy, so it reduces to the analysis of the Bruch-Hautil's building basically. So if you look at the formal model of these spaces, though we are in dimension 1, so these coverings actually have semi-stable models. And if you look at the semi-stable models, of course, this is tight, so the components are irreducible and proper. And this smoothness, basically all of these properties here arise from the combinatorics and geometry of that semi-stable model. But you have to input block-cutter results to it. That is, this can be computed. This is basically computation of p-adic nearby cycles, and p-adic nearby cycles can be computed. They can be filtered by block and cut-on. So block and cut-on give you a filtration of p-adic nearby cycles, and the graded pieces are of the type fp omega or something like omega log. And now you are really on the special fiber of the model. Remember, the model has irreducible components which are proper. So you're looking at cohomologies of something basically coherent of proper objects. So on every irreducible component, you have finite dimension, and then you have to glue this information together. This finiteness comes basically from that. This finiteness. So that's reasonably simple. That's just not the admissibility. Not even admissibility comes.
Because the possibility is for GL2. The whole finite.
Sorry. So Gabriel is absolutely right. Sorry, I misspoken. Okay. Everything here is, that's right. Sorry. Right? Absolutely right. So this is outside of admissibility. This is reasonably easy theorem with having block and cut, right? Now the more difficult theorem. So let me state it as 5 here. Is that finite length. Finite length theorem which will apply admissibility. And now actually this uses global input. No, sorry, of course, you're right, absolutely. Finite length. And so let me just mention that basically the reduction is reduced to properties of the Scholze functor, of Scholze's functor, and there are a couple of things one has to prove. Admissibility of the Scholze functor, but we know that by Scholze actually. But then you have to prove properties of something like that. Galois, let's see what is the precise statement. Okay, so you have to prove that difficult statements. So to prove that the set of smooth, irreducible Fp bar G representations pi such that S1 Scholze pi GK 0 is finite. Zero is, so of course, it's finite. So one of the statements that you have to prove is that. And perhaps if you recall, so you've seen statements like that in the work of Paškunas, I mean Ludwig, maybe Paškunas, Ludwig, Scholze, also original. So they did this kind of computation for the principal series associated to characters, and this K now was coming out. The characters that were allowed, for which this was non-zero, were the ones which were factoring necessarily through the field extension here, which you fix this K. So in step 1, there are 2 things. One is these combinatories of Bruchatetti's buildings, which is reasonably easy via block-cutter analysis of p-adic nearby cycles, and global arguments, which gives you the finite length, which is difficult and which, as Gabriel said, fails.
I shouldn't that mean it socially useful to that really well.
Yes, I should do that. So there is also, I mentioned geometric input, but Gabriel says I should also mention the representation theoretical input, which is the work of Schotten. Someone else? Schotten? Okay.
Okay, thanks.
Actually, I think you had a little bit more time, but
Oh, I still have time. Okay. So I don't know why I thought I had to finish.
just if they are last.
Yeah, I know. Let me just mention one more, because I don't know. I thought I had an hour and 20 minutes. Then I would have hurried this. Okay, well. Let me just state the result on work in progress. It's just like 3 minutes. So on finite level, you only see this. You've seen, I assumed Hodge weight 0, 1, and on whole bunch of things there. But if you go to infinity, you should see everything. So let me just mention what happens sub 3. Completed cohomology. All right, so this is in progress. So now we are looking at infinity, let's call it that way. We are looking at etale cohomology at infinity. But torsion, then we complete, invert P. And this is, of course, inductive limit of finite level cohomologies. So now this has G, D star, so G check, and Galois action, and theorem. So let me just mention the pointwise results. So P supercuspidal, admissible, representation of G over L. So then the Scholze functor is going to split as the V of P, so that's Colmez's functor, and so that's Galois representation, and the Jacques Langlands of P, Jacques Langlands at P of P. And so Jacques Langlands is just defined. So I think Pashkun has already talked about this, if I remember correctly. What did I write here?
But
Yes.
because you will correspond to B,
What does supercuspidal mean?
alpha method captured.
Reducible, yeah, okay. And pointwise result. So now pointwise result. Home Galois of V in the RAM is pi dual and the Jacques Langlands. It should be written. Right. So the main difficulty in this general setting is that the deformation rings are now just much more complicated. Another is the understanding of the Jacques Langlands functor, which appears here, but I think maybe also Pashkun has already talked a little bit of how it behaves in the case. I have put some assumption here. I forgot to put some. So this is in the case maybe generic or very generic. Let's assume V pi generic here. Maybe it's enough for this statement. maybe if you want to understand the Jacques Langlands better, you need really very generic, like Pashkunas was saying. Okay, so the point is that now you see all the representations appearing at infinity, and they also glue, but this is now much more complicated than it was for these p-adics, which we had on final 11.
Okay, thanks.